Okay, so we left off with the question, what does this Laplace transform stuff have to do with solving differential equations, right? So now we're going to actually use this to solve a differential equation. Maybe not this one in particular, but just to give you the idea, suppose you have something like y double prime minus, 6y prime plus 10y equals e to the negative 2t or something like that, right? And typically, we're going to be solving initial value problems. So we will be given the initial conditions. Let's say y of 0 is 0, and y prime of 0 is, I don't know, 5. Right? So again, this is just an example of something that we've done before. Maybe not this exact one, but we've solved very similar ones using a whole host of techniques, right? And this is just one more technique. This is just one more way to do it. And so here's the procedure, right? Here's what we're going to do. Well, we have our what we're looking for. We have our differential equation here, right? And we're trying to solve for y of t, right? That's our goal. So the first step is to apply the Laplace transform to both sides of the equation, right? So look what happens when you take the Laplace transform of the left side. You get the Laplace transform of y double prime. You get this thing here. And the Laplace transform of y prime is just this. And, well, the Laplace transform of just y, even though I didn't write it, right, is capital Y as a function of s. Yeah. So what happens then is you get an equation involving this capital Y here, right? Capital Y of s here. And, in terms of y of 0 and y prime of 0, these are just numbers, by the way, right? These are just numbers. And, of course, s is our variable here. But we're treating the y as what we're solving for, right? We're solving for y of s. Oh, I keep using the wrong color here, right? Well, we're trying to get y of s, and it's going to be some function, right? Some function of s. Let's say it's s plus 8 over s squared minus 9s plus 8 or something like that, right? So you have this. Obviously, this does not solve the equation, right? This is capital Y. We're looking for little y, right? Yep. So okay. So back up a second, right? Step 2, of course, is to solve this equation for y, right? And that's maybe solving a quadratic equation or something. It's not hard, right? That's not the hard part about this, right? The hard part, though, is once you get your capital Y, how do you find little y? And that's step 3 here, right? That's taking the inverse Laplace transform of this thing on the right, the capital Y, in order to get little y, right? Lowercase y, because that's our goal, right? So this here is our step 3, applying the inverse Laplace transform, right? So you can see that this looks like a tedious process, right? You're applying the Laplace transform, converting it to solve for y of s, and then applying the inverse Laplace transform. It's like, so you're going backwards to go forwards. And so, so this does not seem all that simple. Obviously, you already have some techniques for solving equations like this. With the initial values, of course. That's the easy part, right? But once you get used to this process, you'll see it kind of works all at once, right? That you don't have to find any, particular solutions, complementary solutions, all that stuff. It's none of that is necessary here, right? If you're going to do it using the Laplace transform method here. So, right, so that's the idea. And so why don't we just do our first example, and we'll follow this procedure, and we'll see how this works. Again, I'll start with a relatively easy one. So let's suppose we want to solve, let's just do, dx by dt plus 2 times x equals, e to the negative t. And our initial condition will be x of 0 equals 0. Okay. Now, obviously, this is one that you know how to do. This is a first order equation, so just go back to chapter 2 and look at the methods for that. But let's do it using Laplace transforms. In fact, you know, it'll say, right, using the Laplace transform. So just another way to do it. All right. Well, let's start with step one. We want to take the Laplace transform of both sides. So this is just x prime, right, plus 2x on the left, and e to the negative t on the right. Okay. Well, on the left side, x prime, or y prime if you like, is just going to be, oh, yeah, maybe we should note that this is linear, right? So you're doing the Laplace transform of x prime, right, plus 2 times the Laplace transform of x. Right? So, yep, for x prime, if you look straight up at the very top left, you get s times, I'll call it capital X of s, minus little x of 0, right? So that's L of x prime. And then plus 2 times L of x, well, that's just x, capital X of s, right? All right, now what's the Laplace transform of e to the negative t? Well, I guess I'll have to remind you, the Laplace transform of e to the at was just 1 over s minus a. And so here a is negative 1, which means this will just be 1 over s minus negative 1, or s plus 1. Okay, so that's step one, right? We took the Laplace transform of both sides, right? Step two, now we have to solve this equation for capital X, right, of s as a function of s. And in fact, you can suppress the of s, right? Because we know it depends on x, right? So s times x minus, oh, what's x of 0? X of 0 is 0, right? That's our initial condition. So right away we can just, we're subtracting 0 here. So let's move on to plus 2 times capital X. That's just 1 over s plus 1. Okay. So yeah, we're already solving for capital X here. Factor out the s plus 2. This is 1 over s plus 1. Right? And yeah, divide by s plus 2. Right? So x, and I'll put back the s now. X as a function of little s is 1 over s plus 2 times s plus 1, or s plus 1 times s plus 2, either way. Right. So there we go. There's our, well, again, well, okay, that's not our solution, of course. That's just x as a function of s. But that was step 2, right? So that's all it is. It's just a little bit of algebra, right? Step 2 is some pretty basic algebra here. Not hard to do in most cases, right? All right, now comes the hardest part, step 3. So to remind you, step 3 is to take the inverse Laplace transform. Right? So remember, our goal is to solve for little x as a function of t. What we have is capital X as a function of s. So remember how this works? Right, to find, right, we're going the other way, right? We have capital X, we want little x, so we need to apply the inverse Laplace transform, right? So in other words, little x is going to be the inverse Laplace transform of capital X. Okay, so, yep, we just need the inverse Laplace transform of 1 over s plus 1 times s plus 2. And if you're wondering why didn't I multiply that out, well, maybe remember because there is no generic formula for the inverse Laplace transform of something crazy like this. Instead, we want to think of this as a sum or difference. So we might want to split this up as partial fractions, right? A over s plus 1 plus b over s plus 2. And, well, this one's about as easy as it gets, right? But let's go through it. Let's go through it one more time, right? Oh, what does this equal? Yeah, I'm sorry. Yeah, so, hang on. Yeah, okay, so, yeah, so I'm a little bit confused here, but this is, yeah, this is just partial fractions here, right? Yeah, so this is 1 over, I was missing the 1 over s plus 1 times s plus 2 equals a over s plus 1 plus b over s plus 2. So when you multiply both sides by the denominator, you just get 1 is equal to a times s plus 2 plus b times s plus 1. Right, so yeah, so if you plug in your s equals -2, you get that 1 is equal to, 0 times b, and then -2 plus 1 is -1, so b is -1. And if you plug in -1, then this is 0, and you get a times 1, so a is 1. Okay. Yeah, again, we probably should have just guessed that, right? A is 1, B is -1. Yeah, well, okay, maybe not, but yeah, so this is just 1 over s plus 1 plus -1 over s plus 2, right? And so, right, so now we can take the inverse, well, I need maybe a little more space here. Go way over here. So we still need the inverse Laplace transform, right? Now we know what A is. A is 1. And B is -1, so I'll just put -1 over s plus 2. Right? And inverse Laplace transform is linear, so we can split this up. Just like that. And hopefully you remember, yep, I have it up here, right? 1 over s minus a, the inverse Laplace transform would be e to the at. So this is not s, so this is s minus -1, right? So here a is -1, and this is s minus -2, so a is -2. So the inverse Laplace transform of 1 over s plus 1 is just going to be e to the -1 times t, or just e to the -t here, right? And then minus e to the -2t. Right. And there we go. That's it. Right? That's the solution. So let's write this down. Little x of t, right? Little x of t is just e to the -t minus e to the -2t. Make that a little bit neater. So that's the solution to, let me scroll back up a little bit here, this equation right here. So let me copy it down so that we know which equation we were talking about, right? So remember, we were trying to solve x prime plus 2x equals e to the -t with this initial condition that x of 0 is 0. And there you go. There's our solution. Now, you might say, well, in the amount of time that I took to do all this, that I solved it by, either variation of parameters or, actually that's for second degree, but the similar one to this, by an integrating factor, right? So you could have solved this by an integrating factor from chapter 2. But again, not, probably would be easier to do it that way here, right? On the other hand, once you get used to this, because you're solving this equation here, which is just algebraic, right? And we got this solution, then it's just a matter of taking the inverse Laplace transform. And sure, that might involve partial fractions, as it did in this case. But sometimes you don't even have to do that. Sometimes it's just pretty direct what the inverse Laplace transform here was. So yeah, notice at no time did we have to solve for the C1 and C2 here, right? Using the initial condition. Actually, there's just a C1, right? I forgot this is first order. The C2, I really should call A. That's the particular solution, right? As it turns out, the particular solution is just e to the negative t. But, we didn't, that would have been obvious had you done it using that method. So obviously this is a good example just to start, but we'll do a couple more maybe. Particularly, we'll do second order equations, just using this method here. Okay, so that's how this goes. I mean, it takes getting used to this three-step process here, 3 steps. But once you get used to it, solving initial value problems is pretty routine. Now, you might ask, well, what if we don't have initial conditions? What if it's just to find the general solution? So, you notice from the way up here, for the Laplace transforms of the derivatives, this y of 0 then would be, that might be your C1, right? And then this might be your C2, or at least related to some of that. So you're going to have to treat those as constants then, and just label them as some sort of a constant. And that might make the inverse Laplace transform a little bit more difficult, but in some cases it is doable, and in other cases it's just too tedious. So we're going to be focusing on initial value problems pretty much exclusively here. So I wouldn't worry about finding the general solution. Obviously, you could have done that for this problem here. Find the general solution without the initial condition. But again, that's, this is just giving you another option here. Okay, so let's go on to a second example, and I think I'll have enough space here. So example 2. All right. Let's make this a familiar one. How about y double prime, so second order, plus, I'll call it k squared times y equals 0. And my 2 initial conditions, right, because it's second order, I need 2 of them. Y of 0 will be 0, and y prime of 0 will be 1. Okay. Again, this is one that you've solved probably hundreds of times by now, right? This is not a hard equation. This is your, this is your simple harmonic motion. If you remember, we used to call this k, we called it omega squared, right? So this is the angular frequency. So don't get confused with k. If we just call this k, then k would be, m omega squared here. So your omega squared would be k over m. If you go back to your chapter 5, that's where we talked about this. But in any event, this is just the, simple harmonic oscillator problem. And so we're going to solve this by taking a Laplace transform. So we'll take step 1, take the Laplace transform of both sides. So y double prime, and we know this is linear, right? So we can split it up right away. And the Laplace transform of, Laplace transform of 0 is still 0, right? We did that. That was the very first example we did in 7.1 in the last section, right? So what's the Laplace transform of y prime? Well, it is way up here, but I guess I'll remind you of it. It's s squared, little s squared, right, times capital Y of s minus s times y of 0 minus y prime of 0. Okay. And then plus k times the Laplace transform of y is just capital Y of s. Right? And the Laplace transform of 0 is, of course, 0. All right, so plugging in the initial conditions, y of 0 is 0 just means that, right, this is 0. And y prime of 0 equals 1 means that this is, well, this is equal to 1 now. Equal to 1. So, yep, let's do that first. We get s squared times capital Y minus 1, and then plus k times, oh no, k squared. I'm sorry. This is k squared times capital Y equals 0. So I think you can solve for, again, we're solving not for s, for capital Y, right? Yeah, it's add 1 to both sides. You get s squared plus k squared, right, times y equals 1. And so y, as a function of s, is just going to be 1 over s squared plus k squared, right? Yeah, I think that's it, right? So that was step 2, right? Step 2 is to take this equation and solve for capital Y. And remember, capital Y is the inverse Laplace transform of, oh no, sorry, capital Y is the Laplace transform of little y. Right. So now, to get little y, we just apply the inverse Laplace transform of capital Y. Right. Or in this case, we take the inverse Laplace transform of 1 over s squared plus k squared. And that one should be familiar, right? Well, maybe not quite, right? So there's a little issue here. We know the inverse Laplace transform of k over s squared plus k squared is just sine of kt. The problem is that this is a 1, not a k. So you know what you have to do, divide by k. Right? Yep. So that's it. So little y of t is equal to 1 over k times the sine of kt, which should not be surprising because it is, right, it's simple harmonic motion, right? It's a pendulum or a mass on a spring. Just goes back and forth, right? This is a pure harmonic motion. There's no damping, right? There's no y prime term, so there's no damping, and there's no force term here, right? So it's not a driven oscillator. So, you know, yep. So if there's no damping, there's no friction or viscosity at all. It's just going to take this sine function forever and ever. And there you go, right? So again, this is one you could have done by elementary means in chapter 4. But you know, this way works just as well. Right? So I think we probably should do one more. Yep, one more example, and then maybe I'll just mention a few more things. But we're almost done here. There's not much left to do. Okay, so I'm gonna have to erase this and start all over. Okay, scroll on up here. So yeah, so example 3. Suppose we want to solve. Again, I'll make it another second order. Let's use x as our variable. X double prime minus 3x prime plus 2x equals, I'm going to do 6 times e to the negative t. So sort of reminiscent of the first one we did, but, you know. And then the initial condition. So x of 0 will be 7. And x prime of 0 will also be 7, right? Yeah, so this is also a harmonic oscillator, but it's one with a damping term here and an external force, right? An external driven force here, right? And so we've done these before, right? But now we're going to use Laplace transforms to solve it. And so let's see how it works, right? So step one, take the Laplace transform of both sides. So x double prime. And again, because it's linear, we can split it up. Minus 3 times the Laplace transform of, sorry, my little braces here, a little sloppy. There we go, of x prime. And then plus 2 times the Laplace transform of just x. And then that's going to equal 6, because that's a constant, times the Laplace transform of e to the negative t, which I hope you remember. But all right, so that gives us an algebraic equation, right? That gives us s squared times capital X, and I'll suppress the of s, right? Minus s times x of 0, little x of 0, minus x prime of 0. Right? So that's just the first term here. And then we have minus 3 times s times x minus, I was going to say f of 0, but it's x of 0, little x of 0. Right? And this is capital X. Yep, and then plus 2 times capital X. And that equals 6 times, so I gave you some time to think about this. The Laplace transform of e to the negative t is 1 over s minus negative 1, right? So s plus 1. Okay. All right. So step 2, we want to solve for x, capital X, right? Capital X. I know I should do that, but all right, capital X, good enough, right? And so while we're doing that, in fact, right now, before I try to do that, I'll just leave this as s squared times x minus s times x of 0, but x of 0 is 7. So that's minus 7s. And then minus another 7, because x prime of 0 is also 7. And then minus 3 times s times x plus, right, we're distributing negative 3 times negative x of 0. So negative 3 times negative 7 is positive 21. And then we have the 2x. And then on the right, we just have 6 over s plus 1. Okay, so this is not looking too pleasant here, but let's factor out the capital X. So we have s squared minus 3s, right? All times x, and then plus 2 times x. All right, so now what's left over here? Well, we have minus 7s, and then we have just the constants here. We have negative 7 plus 21 is negative 14. All right. And I think that's everything on the left. So this is still 6 over s plus 1. Right, so we can bring this over to the other side, add the 7s and the 14. So this is 7s plus 14. Oh, you know what? Why don't I just factor out the 7? Right, so this is going to be 7 times s plus 2, right, minus 6 over s plus 1. Okay, the only thing left to do now is divide both sides by this s squared minus 3s plus 2, which, by the way, you can factor, right? This is going to be s minus 1 times s minus 2. I think that's it. Hang on. No, that's not it. Okay, negative 7 plus 21 is, positive 14. Right, so when you subtract, you get 7s minus 14, which means this should be a minus 2. Yeah, I thought something canceled here. That's why I was a little unsure here. Right. Oh, and don't forget, you got to do it to both terms here, because you're dividing the whole thing left and right. So here you get s minus 1 times s minus 2 as well. Okay, That, I think, is correct. These can cancel here. Obviously, these cancel, right, on the left. And I think that's step 2. We have our capital X, rather, of S. And it's just going to be 7 over S minus 1. And then minus or plus? Plus, right? Yeah, plus 6 over, this entire mess here, right? S plus 1, S minus 1, S minus 2. Okay. Well, yeah, this we're probably going to have to split up by partial fractions. And while we're at it, why don't we just combine these into a single term here, right? So this is going to be 7 times S plus 1 times S minus 2 plus 6 all over S minus 1, S plus 1, S minus 2, and, well, any order is fine here. Yeah, I think I want to reverse it. We'll make this S plus 1 times S minus 1 times S minus 2. All right. Well, unfortunately, we gotta multiply all this out here. All right. So what do we get? 7s squared, and then minus 7s, and then minus 2 times 7, so minus 14. I think that's right. Plus 6. All over the same denominator. I'm going to get sick of writing it, but there it is again. Right, so the numerator will just be 7s squared minus 7s minus 8 over same denominator, right? Okay. Well, there we go. Now comes the partial fractions. I don't think that's avoidable here. So we'll split it up as a over s plus 1 plus b over s minus 1 plus c over s minus 2. Okay. All right. And then when you multiply both sides, I'm going to do this in green so I don't get completely mixed up here. 7s squared minus 7s minus 8. So that's going to be a times s minus 1, s plus, minus 2, plus, b times s plus 1, s minus 2, plus c times s plus 1 minus 1, s minus 1, right? So, again, this should be very quick, right? In fact, the book just says do the cover-up method, and that works perfectly well here, right? So if s is 1, then this is 0 and this is 0, so we solve for b. Okay, we'll solve for b first, I guess. So if s is 1, you get 7 minus 8, so negative 8, is going to equal 0 plus b, and then this is b times 2 times negative 1. So I guess that tells me that b is 4 here. Okay, moving on to s equals 2. Okay, so if s is 2, this is going to be 28 minus 14 is 14. 14 minus 8 is 6. And now we're solving for c, so this is going to be c times 2 plus 1 is 3. 2 minus 1 is 1. So it looks like c is 6 over 3 is 2. And then we need a, right? So we need to get rid of the s plus 1. So s is negative 1. And so that's going to be, let's see, 7 plus 7. 14 minus 8 is, that's also 6. Okay. And then a times negative 2 times negative 3. So that's positive 6. A equals 6. So a has to be 1. Again, don't expect the numbers to work out this beautifully. These could be fractions, right? Don't worry if you get 2/3 or, 4 over 7. That can happen as well. Okay, so now we can write our capital S, right, our inverse Laplace transform as 1 over s plus 1 plus 4 over s minus 1 plus 2 over s minus 2. So yeah, that was step 2, and that was not easy, right? That was not simple because it involved partial fractions, right? Or, your favorite method for simplifying this, splitting it up. It's usually partial fractions is the way to go. All right, and finally, last step, step 3, which I've been saying that's the hard part. And it is in some cases, but not in this case. So now we just need the inverse Laplace transform, right? Because we're solving for little x. Little x of t is just the inverse Laplace transform of capital X, which is just this. Right? And we know it's linear, so I'm just going to split it up as usual. Try to do my script L here. So that's 1 over s minus 1 plus 2 times the inverse Laplace transform of 1 over s minus 2. So, yep, nothing fancy here. We're just going to repeatedly apply that the inverse Laplace transform of 1 over s minus a is e to the at. And so that gives us our answer, final answer. So e to the negative t plus 4 e to the positive t plus 2 e to the positive 2t. And that's it. Again, this is one that you still could have done by the methods of chapter 4 or 5. But yeah, you notice you don't have to solve, you don't have to find a system of equations to solve for the a and the b or the C1 and the C2 using the initial conditions. That all got taken care of, right? That's all part of this. So, right. So I hope this helps. This is something you're going to do for homework and certainly in your problem set. There's a couple of these in your problem set. Not much harder than this. In fact, if I remember right, I think I gave you one very similar to this, I think with the plus sign. So you can model your solution for that based on this. It's very similar. Obviously, you're going to get different numbers here. And the forcing function is not this. I think it's just t, but I'm not sure. So again, all that, the different forcing function and different coefficients will give you a different solution, obviously, as well as the different initial conditions as well. So keep that in mind. But this is the process of solving differential equations using Laplace transforms, right? So I hope it was worth it. I hope all those Laplace transforms and inverse Laplace transforms, right, that we talked about, was worth it, because now it greatly simplifies finding solutions to differential equations, in particular initial value problems. Sorry, I'm trying to use my mouse to do that. Initial value problems, right? And I don't think in the homework or on any problem set or any test I'm going to give you, if I say that you have to use the Laplace transform method to solve the equation, A, it's going to be doable, it's going to be reasonable, and B, it's going to be an initial value problem. It's not going to be find the general solution. So I hope that helps. Again, you still might be left with the question, why bother with any of this if we learned how to do this in chapter 4? Why are we bothering? So it's true. Again, you can think of this as just an alternative method. It's just another way to solve the same problem. The real power in this method, however, is something that we're not really going to touch upon. I mean, I suppose I could mention it a little bit here, but it's not one that's going to be officially a part of the course here. So let's say we had the same problem here, x, but instead of, was it 6 e to the negative t, right? 6 e to the negative t. Instead of that as being the forcing function, suppose it's something a little more complicated or a little more weird, right? So it might be, let's say, I don't know, how about t plus 2 if t is less than 3, and it might be, let's say, sine of 4t if t is between, let's say, 3 and 5, and let's say it's 0 if t is bigger than 5. Okay, so sure, you can do this using the methods in chapter 4 and 5, but the non-homogeneous part here is a lot more complicated. So you would effectively have to figure this out 3 different times, one for each, well, 2 different times, right? Obviously the 0 is the homogeneous part, but for the other 2 times you're going to have to essentially find 2 different particular solutions, or use variation of parameters twice, or some method. It's not as pleasant, right? And it turns out that this method of Laplace transforms makes this a lot easier. This process becomes much easier, assuming that you can find the inverse Laplace transforms of these functions. Obviously 0, you can always find that, right? And sure, just by linearity, finding the inverse Laplace transforms to these is not that hard. Okay. Now, when you actually, again, don't do this because I didn't, the numbers might not work out very well. The point is, if you go on to 7.3 and 7.4, they give you a whole host of devices that will greatly simplify this. In particular, what the book calls the unit step function, I would just call h, because we haven't used h here, right? This is just the step function, so it's 0 if t is less than 0, and it's 1 if t is greater than or equal to 0, right? In other words, it's just a function that, I'll call it h, right? So when t is negative, you're just at 0 here, and then when t is positive, you step up, and you just become 1 after that, right? So the book calls this the unit step function, right? So this is the unit step function, which makes sense, because it just steps up 1 unit. Other books calls this the Heaviside function. It's named after, Heaviside. I think it's Oliver Heaviside. So Heaviside did a whole lot more than just a step function. I mean, that's kind of a boring thing to be named after here. In fact, you could just call it the unit step function, as some books do. But Heaviside was given the credit for this, and he should have been given credit for a lot more, as it turns out. This was late 1800s, I think, early 20th century maybe. He did a lot for transmission lines. And in fact, he came up with the whole idea for the telegraph way back in the day. Heaviside, I think, also came up with the idea that in the upper atmosphere, there are these currents, or these charged particles, and long before they had any experimental evidence for it. So it's like a couple decades later, they did some experiments and found that, sure, in the upper atmosphere, there are these charged particles, right? But these days we call it the ionosphere. I think that's spelled right. Ionosphere? Yeah. So he came up with he predicted that long before they did any experiments that were able to determine that indeed we have something called the ionosphere. In any event, so that's Heaviside, and so that's the step function. And you know what? Instead of going on about this, let me just leave it at that and say that yes, you can use the idea of this to help you rewrite this function here in terms of the unit step function. And based on that rewriting, it's a lot easier to take the inverse Laplace transform of functions like this when they're piecewise continuous. So, yeah. So again, if you want to know about that, great. Go ahead and read ahead, 7374, but I'm not going to, obviously not going to test you on any of that. So as far as questions that I can ask, of course, are questions like this, right? Very reasonable. And I hope this helps. So I think we'll leave it at that for this section.